When we start to exercise, you immediately increase your activity level, and therefore you're doing more work. Okay, and we've talked about this before. When you do more work, you need more ATP. Okay, and in order to get more ATP, we need more oxygen. So whenever you start to exercise, you increase the demand for ATP, you increase the demand for oxygen. And then your control systems, your central nervous system, your SNS, and your hormones, epi, norepi, and glucagon, all of those work together to meet this increased demand. So you're going to increase your ATP supply. If you didn't increase your ATP supply, you wouldn't be able to do the work. And you also start to increase your oxygen supply so that you can make this ATP aerobically. Whenever demand and supply are equal, we call that homeostasis. Okay, so if the body requires a certain amount of ATP and you're able to supply it, then that would be homeostasis of ATP. Same thing is true with oxygen. Okay, if once your oxygen supply is equal to oxygen demand, then we would be at exercise homeostasis in terms of oxygen. However, oxygen supply does not immediately meet the oxygen demand. So when you start to exercise, jump on the treadmill, your oxygen demand goes up immediately, but your oxygen supply goes up gradually. Okay, so for a period of time, the demand for oxygen is going to be greater than what you're able to supply. And over time, as you increase your breathing rate, you increase your heart rate, the muscle cells start to take up more and more oxygen. Eventually, supply and demand will be equal, and eventually you'll reach steady state. But until you reach steady state, you're in something called oxygen deficit. Okay? Oxygen deficit means that the demand is greater than the supply, and you can quantify deficit by subtracting the actual demand, taking the actual demand, subtracting how much you actually supplied, and then that's going to be your deficit. Okay? And over time, that deficit is going to get smaller and smaller until supply and demand are equal. Then you're in homeostasis. Okay? And I'm going to show this on a graph, and I think it'll make a lot more sense on a graph rather than the words. But before we go there, I want to just say, despite insufficient oxygen supply, we're still able to meet the ATP demand. Okay, so like I said, ATP demand goes up immediately, and we're immediately able to supply it because you're able to keep up with the treadmill. Okay, but the oxygen supply is gradual. So how are we able to meet the new ATP demand immediately despite the oxygen supply lagging? Okay, well, the answer is because we can rely on the anaerobic systems. Okay, so while we're waiting for the aerobic systems to get going and to catch up and to be able to supply the new demand, we rely on anaerobic systems. So here we have a graph with very, very valuable information. I can't say enough how important it is for you to be able to draw this graph, label this graph, and understand this graph. So on the x-axis we have time. Okay, so this is an individual who is exercising. This is when they start. This is when they stop. Okay. On the y-axis, we have oxygen consumption or oxygen use. And so before exercise, we're starting at rest. Okay, resting oxygen consumption is not zero. Resting oxygen consumption is usually about 3.5 milliliters of oxygen per kilogram body weight per minute. Okay, so here we're at about 3.5. The number doesn't really matter, but I just want you to understand that at rest, we are consuming some oxygen. So here we start to exercise, and immediately the oxygen requirement goes up. Okay, so the second you jump up on that treadmill, your oxygen requirement goes from here to here. Okay, so, or demand, you can think of it as demand. Okay, but when we look at actual oxygen consumption, this is the solid line, you can see that actual consumption comes up gradually. Okay, so here we are a few minutes into exercise. Here's our requirement, but here's our actual supply, okay, because it takes time. So as time goes on, our supply, which is this red line, increases. Okay, and eventually supply and demand are equal. Okay, and that's where we reach steady state. Okay. But in that time that it took us to reach steady state for the oxygen to supply to catch up to the oxygen demand, we created an oxygen deficit, and that's what this shaded area is. Okay. This is oxygen that we theoretically needed, but we were not able to supply. And therefore, during oxygen deficit, we rely more heavily on the anaerobic systems. Okay, so as time goes on and the oxygen supply increases, we can rely less and less on the anaerobic systems, and then once we get up to steady state, the anaerobic systems are going to be very minor contributors because the aerobic systems are up to date. So we continue at steady state. We can do that for a while, and then in this example, they end. Okay, so here you jumped on the treadmill. Here you're getting right off the treadmill. Okay, you're going to sit in a seat. Okay, so you're on the treadmill, you're sitting. So theoretically, you're back at rest. Okay, theoretically, you're back. You're not doing anything. Your muscles aren't contracting. You're relaxed. But what we see is that oxygen use doesn't go back down to zero immediately. Okay, oxygen use, okay, or oxygen supply, same thing, comes down gradually. Okay, and eventually your oxygen consumption goes back down to rest values. But there's a period of time there where your oxygen consumption is still high. Okay, so when you get off the treadmill, your VO2 doesn't go back down to resting values immediately. It comes down very gradually. Okay, and this period of time we call Epoc, which is excess post-exercise oxygen consumption. Okay, and it represents the shaded area where, again, theoretically we're back at rest, so theoretically you would think that our oxygen consumption would be back to resting values, but it's elevated. It's elevated for a while, but eventually comes back down to rest at the end of recovery. So if you're sitting in a chair, your muscles aren't contracting, what's going on? What are we using all this oxygen for during recovery? Okay, and that's Epoc. So let's talk about Epoc. So this is during recovery when your VO2 is elevated and it remains higher than what you were at for rest. And basically, there's a lot of things going on during recovery that require energy. So no, you're not on the treadmill, your legs are not moving, you're not doing the work of exercise, but your body is doing the work of recovery. Recovery takes some energy. So some of the things that are going on, epi and norepi, when you jump off the treadmill and you sit in a chair, epi and norepi are still out there. You know, they got secreted, they traveled, they went out. You know that epi, norepi causes increased metabolic rate. And it takes time for that epi, norepi to leave its effectors and go back to the adrenal gland. So for a period of time, epi, norepi is still out there, keeping the metabolic rate high. Also, as you know, your heart rate is still elevated. Okay, you don't go back down to resting heart rate immediately. So the heart muscle itself is still working hard, so we need oxygen for that. You're still breathing heavy. Okay, so your breathing muscles still need oxygen. You also need some energy to replace ATP and PCR. So when you exercise, you end up with a lot of ADP and P. And so in recovery, we want to replenish our ATP stores, and that requires energy, which requires oxygen. We also want to replenish our PCR stores. So we're going to take some creatine and some phosphate, and we're going to need some energy to create that bond. Okay. And again, this energy is requiring oxygen consumption. We also want to replace oxygen stores. So we'll talk about this later, but when we start to exercise, we start to pull oxygen off of our hemoglobin. So we essentially store oxygen in the body. So we start to borrow from those stores until we're able to bring in more oxygen at the rate that it's being used. So we have to replace that oxygen that we essentially borrowed. We also are going to have increased blood flow because we got to remove the lactic acid that accumulated in the body. We are also going to have increased blood flow to help bring the body temperature back to normal. So basically there's a lot of things happening that require energy and therefore require oxygen during recovery. And that's why the recovery VO2 is greater than the resting VO2. And we call this Epoc, excess post-exercise oxygen consumption. So let's see what happens after training. So if you take the same individual and let's say this is a bout of exercise, let's say it's 20 minutes and they were at 7 miles per hour and they reached steady state in 10 minutes, okay? They reach recovery after 30 minutes, okay? So 10 minutes to recovery, 10 minutes to steady state. Okay? So after exercise, after training, what we see are these lines change. So actually before I draw these, you might want to pause this and think about how do you think these lines are going to change with training. Aerobic training. So what we see after training is that you're able to reach steady state sooner. Okay, so now maybe instead of taking 10 minutes to reach steady state, maybe you can reach steady state in 5 minutes. Okay, so what that means is your aerobic systems get up to speed. And you're able to increase your heart rate faster, you're able to increase your breathing rate faster, you're able to utilize extra oxygen faster, and so steady state comes earlier. And as a result of that, you end up with a smaller oxygen deficit. Okay, so steady state sooner, therefore a smaller oxygen deficit. And then you do your normal exercise, and then when you stop, we also see a change in post-exercise, is that we see that recovery comes sooner. Okay, so everything slows down much quicker, right? Your recovery heart rate, your heart rate recovers much quicker, your breathing rate recovers much quicker, and so recovery comes sooner, and therefore your epoch is smaller. Okay, smaller epoch because recovery comes sooner. You know, and this is something we often use to measure somebody's fitness levels. We have them do exercise, and we measure heart rate, and then we measure recovery heart rate. And people whose heart rates come back down to resting values quicker are more fit, okay, because the body is able to recover, come back down to resting levels faster, which is what the body wants, right? The body doesn't want stress. So as soon as you stop exercising and that demand for work increases, the body's going to do everything it can to get back down to resting levels as soon as possible. And if you do this with training time and time again, the body becomes better able to recover quicker. Okay, so you end up with steady state sooner, smaller oxygen deficit, smaller epoch. And then the last thing I wanted to say is that you won't always reach steady state. Okay. Okay, because steady state is when oxygen demand equals oxygen supply. Okay. But if the exercise is intense enough, if the oxygen demand is greater than your VO2 max, you will never be able to supply it. Okay? So you can reach steady state, we call it submaximal, at submaximal intensities. But once we get up to your maximal levels of VO2, if the exercise is intense enough, you will not reach steady state. Okay, you're going to be always relying very heavily on those anaerobic systems, and you're not going to be able to maintain an intensity like that for very long because you know your anaerobic systems are not fatigue resistant.